Hello and welcome back. In today's video, we are going to solve another heat conduction problem, which will be based on lumped capacitance model. So what does this model says is that suppose we have a body whose temperature only changes with time and does not change with spatial dimension, means it changes from time to time and it does not change from point to point inside the body. So according to this problem, suppose a body is initially at 80 degrees Celsius, which means each and every point of the body is at 80 degrees Celsius. So when we put it in the air, which is at 20 degrees Celsius, the temperature will stop dropping for the body. So after some time it will reach to 70 degrees Celsius, and at that time it means lumped system model says that according to this assumption, after that time each and every point of the body will be at 70 degrees Celsius. So temperature is varying with time, but it is not varying from point to point, which in other words means the temperature stays uniform. So it is a uniform temperature variation with time. It is such kind of problem. Here's a question: when do we know a problem can be a lumped capacitance, can assume a lumped capacitance model, and when is the time when lumped capacitance model is not valid? So for that, from the theory we know we have to find the Biot number, and Biot number is defined as HL characteristic divided by K. So to check whether the body, whether the lumped capacitance model is valid or not, we have to find the Biot number. So for this particular problem, we have H, we have L, but we do not have K. So either we know it obeys lumped capacitance model, or we have to check. If we have to check, we should know the material, and for that we should know the thermal conductivity, and so that we can solve for this. And the criteria is, if Biot number is much lesser than 0.1, the lumped capacitance model is valid. If it is much greater than 0.1, the lumped capacitance model is not valid. So let us, for our case, let us say the thermal conductivity for our body, which is not given, material is not given. Let us say the thermal conductivity is high. So K is given 10, L characteristic length will take the length of the cube, and the thermal conductivity, let us say it is high, it is 600. So this value will be approximately, so this will be 10 times 10 to the power minus 2 divided by 6 times 10 to the power 2. So this will be approximately 0.167 times 10 to the power minus 3, which is much lesser than 0. Sorry, yes, which is much lesser than 0.1. So the lumped capacitance model is valid for this particular problem. So what next we have to do is, since we are now sure that the lumped capacitance model can be applied, now lumped capacitance model says that the temperature will vary only with time. So what is that equation? So that equation is the temperature at any time is equal to ambient temperature plus initial temperature of the body minus ambient temperature into e to the power minus t divided by tau. This is the equation that we can use to find temperature of the body after any time. Now, this equation is straightforward, except that there is tau. Tau is called time constant. Time constant, and its value or its relation is rho Cp, volume divided by Ha, surface area of the body. So what does this tau physically mean? Suppose there are two bodies, one body one body and both bodies are 80 degrees Celsius initially, and temperature of both have to drop to 20 degrees Celsius. If this has time constant tau 1, this has time constant tau 2, and time constant tau 1 is greater than time constant tau 2, it means this body will take more time to cool down, this will take lesser time to cool down, which means this body will cool down faster than this body. This is what time constant means. And when we put this time equal to time constant tau, it comes out to be 63.2%. And it means when we for the body wait for the time equal to the time constant, the temperature that has to drop from 80 to 20, which means the drop is 60 degrees Celsius. That means 63.2% of 60 would have dropped after time equal to time constant. And if we want the temperature to drop 95%, it is when we put time equal to 3 times tau. And if we want temperature to drop almost 100%, so for that time constant has to be 5 times, sorry, we have to wait time equal to 5 times tau time constant. So this was a little bit about the time constant. So let us start solving the problem. So our problem says three things. It says we have the dimensions are given, density Cp is given, H is given, initial temperature is 80, ambient is 20. We have to find time constant, we have to find temperature after 60 seconds and 600 seconds. So let us start with time constant. So time constant is rho Cp V by A H A surface, in which is rho is 2500, Cp is 800, volume is A cube 0.01 cube, and H is 10, and surface area is area of 6 faces, which is 0.01 squared. And when we solve this, this comes out to be approximately 333 seconds. So when we wait, when we place our body at 80 degrees Celsius in the air, which is at 20 degrees Celsius, and when we wait 333 seconds, the temperature would have dropped 63.2%. So what is that? Our drop is from 80 to 20. So drop is 60. What is the 63.2% of 60? It will be approximately 37.92. That means temperature would have dropped 80. It was initially, it has dropped by 37.92. So what we are left with, 80 minus 37.92, it will be 80 minus 37.92, 42.08, 42.08 degrees Celsius. So after time equal to time constant, after 333 seconds, the temperature would have dropped to 40.08 degrees Celsius. This is what time constant means in other words. So we found the time constant. Now we have to find the temperature after 60 seconds. So temperature after 60 seconds will be T infinite, which is 20, plus T initial 80 minus T infinite 20 e to the power minus T divided by tau is 333, and time here is 60 seconds. After 60 seconds we have to find, which means 20 plus 60 times e to the power minus 60 by 333. 60 divided by 333 is 0.18, 0.18. When we solve this, it comes out to be e to the power minus 0.18 into 60 plus 20, it is 70.1, 70.1 degree Celsius. This is the temperature after 60 seconds, and temperature after 600 seconds will be same, 20 plus 60 times e to the power minus 600 divided by 333, and it will be 600 divided by 333 is 1.8. So e to the power minus 1.8 into 60 plus 20, it is 29 point, approximately 29.9 degree Celsius. So when we sum up, what we have is time constant is 333 second. Temperature after 60 seconds is 70.1 degrees Celsius, and temperature after 600 seconds is 29.9 degree Celsius. Now let us solve the same problem with COMSOL Multiphysics and we will compare the results. So we'll open the COMSOL Multiphysics, we'll click model wizard, then we'll select 3D. Now since the temperature varies uniformly, there is no meaning of finding the temperature variation from point to point inside the body, so it can be just a one point. So we can even choose 0 dimension for our problem, because we have to see how temperature changes at any point with the time. So it can be just one point. The same thing will be for all the pointers. So since we have a cube in the problem, so we will choose 3D. Now there is one problem now choosing 3D or 2D or 1D, which is we can have temperature gradients unless our Biot number is much lesser than 0.1, and that Biot number depends on thermal conductivity, and for our problem thermal conductivity is not given, and that's not even required. Thermal conductivity for lumped capacitance models is only required to check whether the model is valid or not. So if we keep any value of the k, it doesn't matter. The result is for our result is for the lumped capacitance model will not change by putting any value of k. So what we'll do is we'll choose very large value of k, so that there are no temperature gradients inside and our Biot number will be much lesser than 0.1. And we know putting any value of k will not change our results, because our result is our t of t equation does not have k, our time constant does not have k, so it's independent of k. So we can choose any value of k. So we'll choose 3D heat transfer in solids and we'll put large value of k to make Biot number much lesser than 1. Now we have to our temperature changes with time, so it is a time dependent study. So we will click time dependent and done. Now our geometry, will right click on the geometry and block. Our cube dimensions are 0.01, so depth is 0.01, height 0.01. We will make it centered, coordinate system centered, and we have this cube of side 0.01. Now after geometry we will leave material. We will define material properties directly inside here, as I have shown in the previous videos. We can directly, if we have to just define a couple of properties, we'll define it directly inside the physics. So first of all, we have solid. In the solid we have these properties k, rho, cp. So for k we will choose user defined and we will choose k very high large k. So this will definitely make sure that the Biot number is extremely smaller than 0.1, so lumped capacitance model is valid. And thermal conductivity, we will keep it according to the problem, which is 2500, and cp we will keep according to our problem, which is 800. Then initial value, initially our problem material is okay, everything is fine. Now initially the body is at 80 degrees Celsius, so 80 degrees Celsius. Then we have to apply boundary condition. Now it will be in the air and the heat transfer from body surface to air will be by convection. So convective heat transfer boundary condition, which is in the heat flux, and we'll choose convective heat flux. H according to the problem is 10, which we can confirm from here. Okay, H is 10 and ambient temperature is 20, and ambient temperature is 20 degrees Celsius, 20 degree Celsius, and we have to apply it. So convection will occur at these surfaces. So boundary condition we have to apply on these surfaces. So all the 6 surfaces I have applied the boundary condition, the convective boundary condition. After that we will mesh it, and then we'll click study, time dependent study, and we will start initially at time 0, and we will go to, since we need 660, so we'll go to 600 seconds, or even let us go to 1000 seconds, and we'll keep time step. Oh, but no, let's keep 600. We have to make sure we get exact points of time to find our temperature. So we'll keep step of 60. So I started time at 0, ended at 600 second, and I am telling the console to calculate the temperatures after every 60 seconds that we need. So we'll compute. Well, when we compute here, well, first of all, we'll change units to degrees Celsius. Let's change color as well. So temperature will make degrees Celsius. Then we will show maximum minimum, we'll show units, we'll show titles. So we now have this progress bar, and we have this temperature. What is the maximum temperature of the entire body? Now what we have to do is we have to find temperature after 60 seconds. So we will go to this time. We have temperature at 0 initially, which is 80, then 60, 120, in the intervals of 120, in the intervals of 60, 60, 60. So we have till 600 because we choose the time range like that. So what's the temperature at 60? We'll click 60, then we'll plot. So this is time after 60 seconds. This is the time 60 seconds. So temperature after 60 seconds is 70.1. If we compare it with our analytical value, which is temperature after 60 seconds, is 70.1, which is exactly the same, 70.1. Now temperature after 600 seconds, temperature after 600 seconds is, we'll choose 600 and we will click plot. And temperature after, this is the time 600 seconds, so temperature after 600 seconds 29.7 degrees Celsius. If we see, it's approximately, very approximately same, it is 29.9. And we know this because of this happens, little difference happens because of the rounding of error. See, when we round off while analytically calculating these values, we just take two decimal places, 2 or 3 decimal places. But these comps or these softwares by default take like 64, 32, more than 60 decimal. They calculate up to, they consider up to like 60, 62 decimal places. So the results will be a little different. So these are called a rounding of errors. So practically we have the same value, 70.1 and 29.7. 70.1 and 29.7. So this was this lumped capacitance heat conduction problem using analytical method and using COMSOL Multiphysics software, and we compared both the results, and they are essentially they are same. So this will be all for today's video. Thank you.